Okay, I figured I would go over the questions you might have on the assignment that you've been working on for the last 2 weeks. So let's just what problem is giving you the most difficulties?
I'm gonna do right now.
Yeah.
I mismanaged my time, so I only got to part way through part 2. Like I did part 1, A and B, fine. But part 2, I had trouble with the not when the charge was in between them, but when it was on the y-axis. I had trouble setting up my ratios and stuff.
Okay, and then you didn't do 3, 4, 5, 6, or 7?
I did not.
Okay.
I'm still going to go over them later, but as far as credit, I can do that.
What's your stats do?
I got to make to 5.
To 5, but not 6 or 7. Okay, so Gila sent me an email asking for extension of time. I will give an extension of time primarily because I think that there's still more instruction I can give to help. We've covered everything, but there's the nuance that we haven't looked at. So you both did number 1, and you feel confident with that?
Yeah, that actually really helped me figure out how to do integrals with space.
Okay, so Gila got all the way through 5. So it's only 6 and 7 that you haven't done. Are you confident on the other ones? No.
Honestly, I fumbled my way through the whole lot.
Okay, well, let's start then just looking at number 2, and I won't work all of these out, but I will talk about the nuances of how to approach them and deal with them. So for number 2, and I will make the hard deadline then next Tuesday. No forgiveness. It needs to be in by class time next Tuesday. Okay, so for the electric dipole, you have 2 charges, one positive, one negative. It doesn't tell you which one is positive, which one's negative, so you can choose. But they are on the origin. So you have, or not on the origin, on the x-axis. So here's our x direction. And the origin is midway between them, so there's the y direction. And for part A, you have a point out here. And for part B, you have a point up here. So the difference is on which of the axes are you sitting, but it's the 2 easy calculations. Anywhere else would be much more difficult than those 2 locations. So you randomly choose which one you want to be positive, which one you want to be negative. So Gila, you're closer to me. Which one do you want to be positive? The one on the right or the one on the left? Right. Okay, so we'll make this one positive, this one negative. If I want to find the electric field here, how should I find electric field? Yeah, they're just 2 point charges, so just use Coulomb's law. There's no calculus in this entire problem. Number 2 is not calculus. And so you're just going to say electric field from the positive charge, and we have this distance is L here. This distance here is also L. And then this distance here is R. So you got to get your distances straight. The distance from the positive charge to point A is R minus L. So it's going to be K, Q, lowercase q, over parenthesis R minus L quantity squared, minus, because the other one has a negative charge, KQ over R plus L quantity squared. What direction? These are vectors. I didn't put direction. What direction should these each be? What direction is the electric field at point A due to the positive charge? Does it go into or out of positive? Out. So it's going to be going away from here. So it's going to be going that way. So that's in the positive x direction. So I put my x hats for each one. Now I have to combine these. And this is the first place where people run into problems. People don't combine them, and then when they do the limit, they get 0. That's why I gave you the hint that the answer for the limit is not 0. So how do I combine these two equations? What do I need to do? Okay, common denominator. So I'm going to factor out the k, q, x hat. And I have 1 over r minus L quantity squared minus 1 over r plus L quantity squared. And I need to find a common denominator, which is going to be r minus L quantity squared times r plus L quantity squared. So this is going to be equal to it's going to be equal to that. Well, this is not as fun as things can be, but it's not hard. If you look at the numerator, the cross terms are the only things that won't add to 0. So the numerator, r squared plus 2rl plus L squared minus r squared minus 2rl plus L squared. So this and this add to 0. This and this add to 0. Right? On the bottom, r minus L squared times r plus L squared is going to be r squared minus L squared quantity squared, because r minus L times r plus L, the cross terms add out to 0, and then I have that times itself. Oh, forgot the x hat. What was that?
Should that be a 4?
Yes, it should be 4. Thank you. So that's, I know I did a lot of the work here. I didn't answer all of the questions. How does this change as R becomes much, much greater than L? What does it approach?
0.
Okay, but the hint says it's not 0. It does approach 0, but it has a different form.
That's the double arrow means it's getting much greater.
Yes, the double means much, much greater.
Approaching L.
No. No. So that's an important distinction right there, is just what that means. If R is much, much greater than L, then R squared plus L squared, that L is insignificant compared to the R.
Wait, is that also supposed to be a minus?
Yes, it is.
Right.
Thankfully, it won't make a difference to my next part, but it does make a difference to your answer at this point. So if R is much, much greater than L, then R squared minus L squared is approximately equal to R squared. And so this will become 4KQ RL x hat over R to the 4th power. And then, of course, you cancel one of the R's, and you have the form it takes at large R. I should not have even said as R approaches infinity, because that's not what the problem says. It's just as if R is much greater than L. So like if the two particles were 1 centimeter apart, if you're a meter away, what's it going to look like? And it looks like, if you cancel the r's, 4kq L over r cubed. So it's not just the normal 1 over r squared dependence, it's L over r cubed. Now, of course, I'm assuming I made no math errors. You need to do your own math just to check. Then we have part B. Part B is looking up here. What direction is the electric field from the positive charge going to be at point B? It points which direction for a positive charge? Point B is this one up here. So from the positive charge, what direction is the electric field always point? Away. And so I'm going to have an electric field from the positive that's like this. What about the electric field from the negative? Toward, so I'm going to have one like this. Based on the symmetry, they're going to have exactly the same magnitude, but one's angled up and one's angled down. You can immediately make a symmetry argument. If you add these two vectors, you're going to have kq over r squared kq over r squared. What's the resultant of those two? It's not 0. Start at the beginning and at the end. It's only in the x direction. There's no y component again. Only in the x direction. And you could, take this angle and find very quickly what proportion of the kq over r squared is in the horizontal direction. It's going to be a different equation, of course, than you found before, but you go through and do the same type of work to find how much is, or what the form is for r much greater than L. So you're doing fundamentally the same work, but different geometry. This one here, you have to add the vectors, but it turns out that adding the vectors is really simple. I mean, you have not in the same direction. Okay, 3 introduces a new problem. The non-conducting sphere. What does it mean if it's non-conducting? Charge can't move. So that means you put charge there, it stays. So this has a charge density throughout the sphere, but it's not uniform. Most of what I did was uniform. So first, what is the total charge on the sphere? Well, I have a sphere, and I need to integrate all of the tiny little pieces of volume in here. Okay. My 3-dimensional picture is not perfect. First question, what coordinate system should I use if I have a spherical symmetry? What did you say? Spherical, okay. I thought I heard vertical, and I was like, I don't even know what that would be. So use spherical coordinates, and to get the total charge, I need to find the total charge is equal to integral of rho is the charge per unit volume, dV is that small piece of volume, over the entire sphere. So that's going to be integral from 0 to 2 pi, integral from 0 to pi, integral from 0 to capital R, rho, which is b r to the 1/2 times r squared sine theta all right. Is this an easy or hard integral? It's a triple integral. Is easy or hard? It's easy. It's easy because that's equal to integral from 0 to 2 pi of d phi. You have to make sure you know which angle goes with which limit. Integral from 0 to pi sine theta d theta. integral from 0 to capital R of r squared times r to the 1/2 is going to be r to the 5/2. And of course I didn't write the b, so I better put the b out here. So we have 3 simple integrals.
This is a solid sphere, not a shell.
Correct, it's a solid sphere. So what is the integral from 0 to 2 pi of d phi? Yeah, that's just 2 pi minus 0 or 2 pi. Integral of sine theta d theta from 0 to pi, integral of sine theta is minus cosine theta. And so that's going to be minus cosine of pi minus cosine of 0. Notice I was very explicit with my signs here so I don't make a sign error. Well, what's cosine of pi? Minus 1. Cosine of 0 is, so minus a minus 1 minus a minus 1 is 1 plus 1. So that's 2. Nice. And finally, we have the green one. Integral of r to the 5/2 is? Okay, you raise the power by 1 and divide by the new power. So you put that all together, and you have 2 pi times 2 is 8 pi. B over 7, capital R to the 7/2. So we were able to calculate the total charge on this here sphere. Now that was part A, just to get our feet under us. Oh, actually, it tells you to plot it. Well, you just plot it. I use Excel for all my mathematical needs. I'm sure there's better ways. Draw the sphere and indicate the infinitesimal volume. So I did that. My infinitesimal volume has dimensions of dr in this direction and d theta in this direction, and the missing direction is actually d theta. No, it's r d theta for this one, and it's r sine theta d phi for the last one. So those are the dimensions of that little piece. You're going to have a hard time, just like I did, trying to mark them on there. But that's my little piece. So what was the expression for the infinitesimal volume? That was the dV, which I put right here. Right? You have to answer all of these explicitly to show that you actually understood what you were doing. What coordinate system we use and why, we talked about that. What's the charge contained within it? The charge contained within it was rho dV. Right, so we answered all of those, but you have to answer them explicitly, not just doing it like I did. Because I want to see that you understand the process that you went through, not, well, I followed along and wrote it down. Okay, so then you write the integral indicating the limits and variables and solve it. Then use Gauss's law. So it tells you which law to use to find the electric field within the sphere. What's Gauss's law? Starts with that. The flux equals the charge enclosed over epsilon 0. So it once again takes you through a lot of steps, but the first thing that you really do when you're solving a Gauss's law problem is you define your Gaussian surface. Your Gaussian surface needs to be a surface that matches the symmetry. So you have, remember I talked about this last week, So you have either the electric field is parallel to the area and constant on the surface, or the electric field is perpendicular to the area. For spherical symmetry, since electric field goes in or out, the only shape that could possibly have that is the sphere that's concentric with our sphere. So your Gaussian surface is going to be a sphere within the sphere of radius lowercase r. What is lowercase r? I don't care, because you're going to calculate the electric field for all r between 0 and capital R using this Gaussian surface. Now, if you're outside, you just have another sphere. So you have really two regions here, one that's inside and one that's outside. What's the difference? If you're inside, the charge enclosed, remember that's charge enclosed, you're going to have to integrate, because the charge enclosed is going to increase as R increases. If you're outside, there's no additional charge, and you're just going to use the total charge if you're outside. So you have two fundamental different calculations, one with a constant Q and one with a changing Q. So what you need to do, so I'm not going to go piece by piece here, but I'm just going to go to, I have my sphere, and I'm going to have Gaussian surface number 1 of radius R1 and Gaussian surface number 2 of radius R2, where we have R2 is greater than capital R and R1 is less than capital R. So I have those two Gaussian surfaces. Now, just to back up one step, Gaussian surface means a surface that I have imagined for calculational purposes. It's not an actual surface then. It's a surface only for calculational purposes. So it's not like you have a real object, you say, no, I can't see that Gaussian surface, right? Because it's not really there, it's for calculation. So now I just have two calculations. In region 1, charge enclosed is equal to, and I can just look back at my first integral because I'm not following everything exactly. Where's my first integral? I can look at my first integral and just say it's going to be this same thing here, except for instead of going to capital R, it's going to lowercase r1. So it's just going to be 8 pi b over 7 r1 to the 7/2 power. So that's my charge enclosed. And then I do the flex. Is the integral of electric field dot dA over that Gaussian surface. But I chose my Gaussian surface, so what was the vector relationship between E and dA? No, they're parallel. The electric field lines have to be radial, and dA is the direction coming out of the surface. And so for a spherical Gaussian surface, the dA is also the radial direction, the direction coming out. So, okay, to make sure that is clear. The electric field lines can only be going in or out. Because this is a positive charge, the electric field lines have to be going like this. Right, electric field lines are radial. And on my surface, dA is the direction normal to the surface coming out of it. And so everywhere on the surface, E is parallel to dA. So E dot dA just equals E times dA. So I've simplified my integral because it no longer has a dot product. How did I simplify it? I have to explain the math. But then the next step, the electric field it's only possible for it to depend on the distance away from the center because you have spherical symmetry. It doesn't matter what angle you look at a ball from, it's going to look the same, right? So your position where you are around it doesn't matter. It only matters how far you are from the center, which means the electric field is constant on a surface of radius r1. So that means integral of E dA, I can bring a constant out of the integral. So the electric field integral of dA, which by definition is just E times the area of a sphere. Area of a sphere is 4 pi r cubed, squared, of course. You'd have the wrong units if it was r cubed. 4 pi r squared. So I used r1 because I'm doing Gaussian surface 1. And so now I have the charge enclosed, and I have the flux. And so I use Gauss's law, and I have, and I should have put a subscript 1 on that too. E1, 4 pi r1 squared equals 8 pi b over 7 times r1 to the 7 halves power. So what is the electric field? That's an epsilon 0. That was a very funny looking epsilon 0 because I wrote r by accident. Um, 7, 5, 3. So that's the form of the electric field inside of this sphere. Now, once again, I did all this math quickly. Hopefully, I didn't make a mistake. Go through and do each part step by step, following the instructions, so answering each of the individual questions. You can look at the rubric to see how I'm going to be grading so you know exactly what you need to have. But there's my electric field equation for any radius inside of the conductor. Now, conductor, insulator, I was thinking a step ahead. When we talked about conductors, what was the electric field inside the conductor? It was 0. But for the insulator, it's not 0. Why? Because in the conductor, the charge was free to move, so it would move around until the electric field is 0. In the insulator, that charge can't move, and so you definitely can have an electric field inside of the insulator. Now then you go outside. What did I say about outside? The Q is constant. So outside, the flux calculation will be exactly the same. You'll just change from R1 to R2, of course. But the Q will be the total charge of the sphere. And so you'll have a 1 over r squared, just like it was a point charge. And then you have to graph what the electric field looks like starting at the center and going out to, I think, 5 times the radius of the sphere. So you're going to have a graph showing what the two functions come together to look like. Any questions about the process there? You guys both have access to OneNote, right? Just making sure, because obviously you'll likely want to look back. What did he do? No questions? Okay, next one. Wow. Yeah. Coaxial cylinders. These are coaxial cylinders that have, in the inner region, nothing. And then between radius A and radius B, you have insulating material that has charge on it. And then outside of B, you have nothing again. So this is easiest to look at from above, that is, two concentric circles. I should have used different colors. So this one has radius A. This one has radius B. Notice my artwork, not perfect. They're concentric. So if these are cylinders, what kind of symmetry do you have? Cylindrical. Very sharp. So since we have cylindrical symmetry, what type of a coordinate system should I use?
Cylindrical?
Cylindrical. Wow, this works out really nicely. So how many regions do I have here? Three regions. I have region 1, so I'm going to make 3 Gaussian surfaces. What were my rules for selecting a Gaussian surface? Okay, I want either the electric field to be parallel and constant or perpendicular. If it's perpendicular, I don't care. So I look and I say, looking at the flat section here, what shape would match the symmetry here? Looking down the cylinder axis, what shape matches my symmetry? Circle. So my Gaussian surface is going to be looking at in this direction, a circle. Looking out from the side, it's going to have to be a cylinder. So I'm going to use a cylindrical Gaussian surface. So this is a top view. And then I'll make a side view. The side view I have, well, let's stick with the same colors. Right, that's a side view. So for my Gaussian surface, I have 3 Gaussian surfaces, one that goes like this. Okay, I usually make them dashed so we realize that they're not actual surfaces. And that one here would look like this, or like this, which here would look like this, or finally like this, which here would look like. Now in my picture, I have increasing heights with the different Gaussian surfaces. That is immaterial. If it's an infinite cylinder, the height of my Gaussian cylinder can't matter. If it's not infinite, well, I've got other problems. We do infinite cylinders, it's an infinitely long cylinder for the problem, because in reality, if I have something like a coaxial wire that's this long, if I'm looking really close to the wire somewhere near the center, it's infinite as far as I can tell. If I get farther away, then it doesn't look infinite. So if you get close enough, it's going to look infinite. So we go in that approximation, just like, well, the last problem for the homework set is essentially the parallel plate capacitor. It's only one plate, but it's the same idea. And we'll get to there. We're going reasonably fast, I think. So now I'm going to have to go through and do exactly the same processes, but now what direction should the electric field be pointing on the surface of my Gaussian, on my Gaussian surface? I'm positive. So it should be radial out. So the electric field is going to be pointing like this. And of course, dA on the sides is going like this. So looking at this picture, electric field's like that. dA on the side is like that. On the top, my electric field is like this, but dA is like that. And so I'm going to have to consider the flux on both the sides and the top and bottom. So I'm going to have the flux is equal to the flux on the sides plus the flux on the top plus the flux on the bottom. So I have three fluxes to calculate. You put them all together and you have the total flux because it has to be a closed surface. Your Gaussian surface is always closed, otherwise how would you have the charge enclosed? So let's do the sides first. What's the relationship between the direction of the electric field and the area? Parallel. So E dot dA is equal to E dA. Based on our symmetry, the electric field has to be constant at a constant radius. So E is constant at constant radius. So the flux, the side, is equal to E times integral of dA equals EA equals the area for the side of a cylinder is the circumference of a circle, 2 pi r, multiplied by the height, which I said doesn't matter, but I've still got to put in the height. So there's the flux on the side. And this flux on the side is going to work for any of the three regions. So I went ahead and didn't put 1, 2, and 3. It's going to work for any of the three regions. What about on the top? What's the relationship between the electric field direction and the area direction on the top? So what's E dot dA then? The electric field is sure as life not constant on the top, but E dot dA is 0 everywhere. And the bottom has exactly the same symmetry. And so I had three fluxes to worry about, but 2 of them are going to be 0. So I've got the flux taken care of, then I have to do the charge enclosed. So the charge enclosed, I'm going to have, you can do this multiple ways. Integral from 0 to A of 0 dV plus integral from 0 to B of rho dV plus integral from B to whatever I am at of 0 dV. Now that would be the charge enclosed if R is greater than B. If R is less than A, what's the charge enclosed? It's 0 because we haven't gotten to where the charge is yet. So I'm only going to have an interesting integral between A and B. And whoops, I put a 0. That should have been from A to B right here. From A to B. So that's the only integral that's going to be interesting. And so you're going to have to do the cylindrical integral. Cylindrical integral, what is dV? dV is equal to whoops. I'm going to change that to phi, so it's the same angle. It's the one that goes around a circle 0 to 2 pi. Because you have r d phi is the length this way, dr is the length this way, and dh, or dz, I guess, is the height. And so you're going to go ahead and do your integral. I'm not going to do the integral here because we have the dv. You can do your own calculus. And so you, once again, set charge enclosed is equal to the flux for each of the three regions to find what the electric field is in each of three regions. The interesting outcome from this is if R is greater than B, it's not 1 over R squared like it is for a point charge. That kind of makes sense, right? A point charge, you would have had 1 over R squared because the charge is coming from a single point. As you get farther, it's just increasing linearly the distance from that point, and you have 1 over R squared. But if you have a wire, such as what you had for problem 1, you have the same result here. The wire, when I'm close, I really only see the stuff that's in a small angle here. Stuff that's way down there doesn't make much difference. If I go farther away, stuff that's farther down is going to make more of a difference. And so as I go out, it's like I have more charge that's contributing. And so that means it's not going to drop off as 1 over R squared because it's like the charge is increasing as I go out proportional to radius. And so it turns out you have a 1 over R relationship for a wire instead of 1 over R squared. Now let's just in our minds extrapolate that. What if instead of a one-dimensional distribution of charge, I have a two-dimensional distribution of charge? So the whole tabletop is charged with, charge. As I move up, I have the distance I'm seeing here is increasing proportional to R, and the distance I'm seeing here is increasing proportional to R. And so my charge is increasing as R squared, and then I have over R squared. What's that going to suggest for the electric field? It's constant, and that's the actual outcome. The outcome is if you have a sheet of charge that's infinite, the electric field is constant regardless of how far away you are. And so that is problem 7. Okay, problem 5. This is the last one you got to, you said, right? So problem 5, we have this electric field function. And it says that we need to first plot it. How do you plot it? You only have one of the constants. There are 4 other constants that you don't know. Just choose numbers for them. Try to choose numbers that makes it look interesting as opposed to, wow, I was able to choose numbers that makes it a flat line, right? We don't want the flat line. Try to choose numbers that make it so it looks interesting. But you can have different variations based on what you use for those constants. Remember, they are all positive constants. So you plot it and then describe your method and then do it. So we talked about this in class. This is the one that I couldn't remember the equation offhand. Well, I looked it up beforehand. And that is our equation, and I'm just going to, here's my solution. I'm just going to make sure that I didn't forget. Right there, del dot E is equal to rho over epsilon 0. So all I have to do is that directional derivative. What is the directional derivative in Cartesian coordinates? So what? Well, you have x hat d dx plus y hat d dy plus z hat d dz. Now I'm doing a dot product, so the electric field vector is only in the z direction, right? So when I do a dot product, I'm multiplying the parallel parts. So the x hat is multiplied by 0. The y hat is multiplied by 0. And I'm just going to have my z hat and z hat dotted together. So I'll have partial with respect to x of that whole thing. I drop off the z hat because I did the dot product. And so you're just calculating that derivative. Boom. It's really kind of quick and easy. I like quick and easy. I hope you do too. We only have 5 minutes left, so I'm going to have to go real quick for the next one. 2 uniform overlapping spheres. These now have constant charge densities. Constant charge density means that the flux, or the charge enclosed, is just going to be 4 pi radius 4/3 pi radius cubed times rho, right? That's how much charge is enclosed because it's uniform distribution of charge. So that makes that part easy. You don't have to do calculus to calculate that anymore. You need to calculate what the electric field is due to each of those two spheres, and then add the electric fields as vectors in the region they overlap. So you have two spheres that are closer than the diameter. You have sphere 1 like this, sphere 2 like that. They're supposed to be exactly the same radius. And one has negative charge density, one has positive charge density, and you're finding the electric field in this region here. So like I said, find the electric field equation due to each one of these spheres, add them up in that region of overlap. It comes out to be surprisingly easy for the answer. The work will take some work, but the answer comes out to be surprisingly easy. So if you get something super complicated, you did it wrong. Yeah.
Can I take a guess at the answer?
Okay.
0?
No.
No.
1.
1?
No, it's not 0 or 1.
1 is more complicated an answer than 0. Just
No, it's not 0.
Is it 0 at the very middle point, though?
No.
Really? Like even? Oh, because one's positive, one's negative.
Yes.
Okay, so I'm going one way or the other.
Okay, now the last one. I want to look at this. You have a slab that goes on forever that has a uniform charge density, and we want to measure the electric field as a function of the height z. This has a thickness of 2d, so here's d, and here's d, thickness of 2d. And so now we look at this and we're like, well, what kind of symmetry do I have here? Clearly I have some kind of planar symmetry here. How do I choose a Gaussian surface that's going to work for this? And there are two obvious choices. You can choose either one of them. What are the conditions we're looking for a Gaussian surface? Okay, parallel or perpendicular. If it's parallel, we want it to be constant electric field. So we look at this. What direction is if that's positive charge density, what direction is the electric field going to be pointing at any location? Okay, I'm going to change your word from up to out. So based on that, what is the electric field right in the center? Right in the center where the dashed line is, what's the electric field? But 0 is right here. Because you're changing from this direction to this direction, it's 0 in between. So the electric field is 0 there, so you could choose a shape that has one edge here, or you could choose a shape that's symmetrical with one edge here and one edge here, both the same distance from the center. Either one works. It's completely up to you.
The surface is what now?
So, okay. The shape that I always choose is a cylinder. I choose a cylinder because the cylinder only has 3 surfaces, whereas a cube has 6 surfaces. And mathematically, it comes out to be just as easy either way. But it's just easier conceptually to say I only have 3 surfaces. So that cylinder, the sides will have their areas perpendicular to the electric field. So the sides will always have a flux of 0. Only the caps can have a non-zero flux. If I choose the one with one cap in the center, then the flux in the bottom cap is also 0, and the only flux that's non-zero is that one. Whereas if I do this, I'm going to have the same flux for the top and bottom surfaces. I'll have double the charge and double the flux. Comes out to have the same answer. So you can choose either way, whichever symmetry fits your mind. But then you have to, once again, calculate the charge enclosed. And this is a uniform charge density, so the charge enclosed is just going to be the height times pi r squared for, well, let's just say area. The height of your cylinder times the area of your cylinder is the charge enclosed. And the flux will just be the area of the cap of your cylinder times the electric field. Well, that becomes real easy. Electric field times area is equal to area times height times charge density over epsilon 0. Cancel out the two areas. You have electric field is equal to height times charge density over height times charge density divided by epsilon 0. And so as you go within the slab, your electric field is increasing linearly. Once you get out of the slab, what do you have for the charge enclosed? How does the charge enclosed change as you get farther away once you're outside? It's constant. And so then you have the heights cancel, the height cancels. You have no change in height anymore, and so it just doesn't change, it's constant. So we are 1 minute over time. There we've gone through how to do each one just to make sure you can do it. Sit down and do it. Please, if you have difficulties, contact me.